The Facultad de Física, and today we have the immense privilege to host a talk by Professor Takaaki Kajita from the University of Tokyo. As you may already know, Professor Kajita has been awarded with the Nobel Prize in Physics in 2015 for the discovery of the neutrino oscillation. Professor Juan Antonio Caballero, our colleague from the Atomic, Molecular and Nuclear Physics Department, is going to present Professor Kajita. Juan Antonio.
Thank you. Thank you very much. So, dear professors, dear students, welcome you all here. I'm really impressed by just this image. It's the first time I see this class so full of people, and even people who have not had the possibility to come. So let me just say a few words about Professor Takaaki Kajita. Just some general information, and then I will show you something basic about his work. So he studied at the University of Tokyo, and he got his PhD there at the University of Tokyo under the supervision of Professor Masatoshi Koshiba, who was also a Nobel laureate in 2002 for the detection of cosmic rays. So from that time, he has been director of the Institute for Cosmic Ray Research for a long period of time, president of the Science Council of Japan, member of Japan Academy. He is also, apart from the projects working on neutrinos, which I will talk a little bit later, he is also the project leader, the principal investigator of Kagra project. He will talk about that. This project is just based on gravitational waves, so it's a different topic. He has been involved for many years, and he is right now distinguished professor, university professor and special university professor at the University of Tokyo. He has received so many prizes and so many distinctions that I cannot list here. Just some of them. For instance, in 2016, he was named Scientist of the Year by Harvard University. He has received the Order of Culture from Japan. This is one of the Japan's highest academic distinctions. In fact, it is conferred by the emperor to people, to individuals who have made outstanding merits, outstanding contributions to science in general, to technology. Of course, he was awarded the Nobel Prize in Physics in 2015. He has been named honorary professor by many different universities, doctor honoris causa, by the way. He will be, tomorrow morning, he will be named doctor honoris causa by of the University of Sevilla. So this is the main reason he's here. So let me just change a little bit, just a few general overview of his long work. He has been focused from the time of PhD on the neutrinos. As you are very young here, but you know that neutrinos are the most abundant particles in the universe, apart from the photons, but yet the most abundant, yet the most elusive particles, the most difficult to detect. So he was working at first in this Kamiokande project. This is an underground detector in Japan. So with this, by the way, this underground detector was designed at first to try to establish the decay of proton, not even for neutrinos. It was designed to study if the proton was not stable. So it was, but at the end, they changed, and then they started to detect neutrinos. And in fact, it was famous because the first time people detected neutrinos coming from explosion of stars, from supernova 1987, was with Kamiokande, and Professor Kajita was in this research team. Then after that, he started working atmospheric neutrinos, or neutrinos produced in the atmosphere, and then he was the leader of the Super-Kamiokande project. It was just the evolution of Kamiokande. Super-Kamiokande detector I think it has been one of the most sophisticated detectors ever constructed. So it is an underground, and it detects neutrinos coming from almost everywhere. So he did very nice, very detailed analysis, and they discovered, for instance, that the number of neutrinos entering the detector from above was different than the number of neutrinos from below, just after passing through the Earth. And they make public these results and this analysis, and it was the point in which they just say that neutrino oscillation was a real fact, it was a reality. So neutrinos change as they travel through space, and because of this, and in order to have this change, they should be massive particles, they have to be mass. So this was in 1998, and several years later, he was awarded the Nobel Prize in Physics for let's say the discovery of neutrino oscillation, which shows that neutrinos have mass. Just a few words, he is a team leader in Japan, but this is important for us as you are students from the University of Seville and professors. We have a collaboration with Japan. This collaboration is just focused on what we call the T2K experiment. This is an experiment also based in this Super-Kamiokande detector, but basically is neutrinos are produced on the eastern coast in Japan. They travel through almost 300 kilometers, and they are detected in Super-Kamiokande just on the other coast. And in this travel of 300 kilometers, they studied exactly how neutrinos evolve, so how they change of what they call flavor. So this is a very international collaboration, and the University of Seville and the group in Seville is a part of this collaboration. So we are now, for the last maybe 6-7 years, just working with them. And in fact, the University of Seville is an official member of this international collaboration, and I think this is important. And just to conclude, he has been the leader of, let's say, very large international collaborations. So you mean that Super-Kamiokande and T2K is hundreds of scientists, engineers, students, professors. So this is a real great project, which is basic, or is essential for basic research. So now, okay, he has been here, so it's a real privilege to have you here, and it's a privilege also for the General University of Seville to have him here in this faculty and in general the university. So thanks for coming, all of you. It has been a privilege also to have you all here. So now is your time. Thank you.
Thank you. No, I think I have this one. Can you hear me? Yes. Okay. Well, first of all, thank you very much for coming to this room. I'm very pleased that so many of you come to this room. Thank you very much. And indeed, it's my pleasure to speak to you about our studies of neutrinos and gravitational waves. Well, let me tell you about the outline of this talk. First of all, in the previous page, you may wonder, what is Kamioka? Well, first of all, I want to tell you the location of Kamioka. Then I want to talk about our neutrino studies, Kamiokande, Super-Kamiokande, atmospheric neutrino oscillations, solar neutrino oscillations, and then I want to talk about the recent Super-Kamiokande activities. And before finishing the neutrino part, I want to talk about the future project, which is called Hyper-Kamiokande. Then I'd like to move on to gravitational waves, and I'm now involved in the Kagura project, therefore I want to introduce the Kagura project, and I'll summarize this talk. So, first of all, you noticed there are many, many topics, and that means I will not go into details. Instead, I'd like to discuss what we have done and what we are doing, what we are going to do in Kamioka. Okay, first of all, location of our experiment. This is the map of Japan, and our experiment is located there in the mountain area. Indeed, the photo in the right side shows our location. Well, in fact, in the mountain, just shown in the right corner, shows the mountain that our facilities are located. By the way, this photo was taken in the 80s, and you see the mountain is covered by snow, and indeed this area used to be famous by extremely heavy snow, but actually nowadays, due to the climate change, the scene is slightly different. Okay, so anyway, let's start. Now, I want to talk about our neutrino studies. The first experiment is the Kamiokande experiment. But before talking about the Kamiokande experiment, I'd like to briefly summarize what are neutrinos. Maybe for this audience, it's not necessary, but maybe some of you may not have a good idea. So let me talk about what are neutrinos. Well, neutrinos are fundamental particles like electrons and quarks. And well, but of course you want to know more, and then I'd like to tell that neutrinos are something like electrons, but without electric charge. In fact, this has a very significant effect. Neutrinos can easily pass through the Earth or even the Sun. And in fact, this is very important because neutrinos can bring information of the fundamental processes at the center of the stars. And in addition, I want to say that neutrinos have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And also, I want to say that neutrinos have been assumed to have no mass. That was simply an assumption. Then you may wonder how we can study neutrinos. In fact, we can never see neutrinos themselves. But we can study neutrinos by studying very rare neutrino interactions. For example, a neutrino may interact with a nucleus. In this case, typically, a charged particle is emitted. And in fact, we have various technologies to observe these charged particles. For example, if this particle propagates in the water, this particle emits photons, which is called Cherenkov photons. And therefore, if we have photodetectors, we can observe these photons. And therefore, by analyzing these photons, we can study neutrino interactions. So this way, we study neutrinos. Now, let's talk about the Kamiokande experiment. As already actually introduced, Kamiokande was originally designed to search for proton decays. In fact, about 50 years ago, grand unified theories of elementary particles were proposed. And in fact, I think this was a very attractive theory. And according to the theory, protons should have a finite lifetime of about 10 to 30 years. In fact, well, 10 to 30 years is very long, but on the other hand, this number tells us if we observe more than 10 to 30 protons for a year, we should be able to observe at least one proton decay. So, therefore, several proton decay experiments began in the early 80s, and one of them was the Kamiokande experiment. And here I showed a sketch of the Kamiokande experiment. It was a water tank detector, and it had about 16-meter diameter and 16-meter high, and it contained 3,000 tons of very clean water. And of course, in fact, this contains much more than 10 to 30 protons in this water. Therefore, the idea was we should be observe proton decay. And when a proton decays, typically 2 to 3 charged particles are emitted, and these particles emit photons, Cherenkov photons. Therefore, we should be observe these photons by photodetectors installed at the surface of the tank, inner surface of the tank. So this was the idea of the Kamiokande experiment. And in fact, well, I was a 22-year-old graduate course student, first-year graduate course student, and I thought that Kamiokande must be a very important experiment, and I joined Kamiokande. Okay, by the way, you cannot buy this kind of detector. Therefore, you have to construct a detector, and I would like to show you one photo when we constructed the Kamiokande experiment. Here, you see 3 people on plastic boats. And indeed, we installed the photodetectors onto the detector wall by using these plastic boats. The idea was, well, 60 meters is very high. If you drop from there, you die. So we didn't want to die. Therefore, we decided to use water and boat. So even if we drop from the boat, we are safe. That's the idea. Anyway, I think, well, we were successful. And after several months of the construction work, we started the experiment. And indeed, I enjoyed these works very much. And also, I was excited because I thought that the data from Kamiokande may contribute to physics much. And around that time, that was first year PhD course, I decided to be a physicist. And I think I was really lucky to be involved in such an experiment that fit to my interest and work style. Well, I was very excited to work in an isolated, exotic place. Well, that was 1,000 meters underground. Also, well, I think I was fortunate because in this kind of experiment, the competition was not serious. So I simply enjoyed the experiment. Anyway, after the successful installation of the phototubes and electronics, we started the experiment in July 1983. Unfortunately, the true proton lifetime was much longer than 10 to 30 years. And therefore, we didn't observe any proton decays. Instead, of course, we observed various other phenomena. And one of the phenomena was observed was the electron signal from the cosmic ray muons that stopped in the detector. And then we looked at the energy spectrum, which is shown here. And this indicated at least up to, say, above 15 MeV, there is no background to the observation of the electron spectrum. And this suggested that neutrinos with the energies of about 10 MeV could be observed. And therefore, Professor Koshiba proposed to improve the Kamiokande detector to observe boron-8 solar neutrinos. That was only a few months after the start of the experiment. And boron-8 solar neutrinos had an end energy of about 14 MeV. Therefore, certainly, well, in principle, Kamiokande should be able to observe solar neutrinos. In fact, there was a strong reason for Professor Koshiba to propose to observe solar neutrinos in Kamiokande. Because before Kamiokande, there was one solar neutrino experiment that observed solar neutrinos. That was the Homestake solar neutrino experiment. However, there was a mystery. The observed flux by the Homestake experiment was only about 30% of the predicted flux by the solar models. People discussed a lot, but we didn't know what happened. Anyway, one of the possible explanation was experiment was wrong. Therefore, we thought it's very important to have an independent experiment that observes solar neutrinos. And therefore, we decided to improve the Kamiokande experiment. Well, it's easy to say improve the experiment. Well, we worked hard for the improvement starting in 84, 85, 86. Then finally, we begin to take low energy data at the beginning of 1987. Then something unexpected happened. On February 23rd, 1987, there was a supernova explosion at the Large Magellanic Cloud, which is a galaxy next to our Milky Way galaxy. And here you see two photos, and comparing these two photos, you find that a star is really shining very, very brightly. So this was supernova. And as I said, well, this was February, and as I said, in January 87, Kamiokande was starting a stable data taking for low energy events. So we looked at the data recorded in the Kamiokande. Then we observed a burst of neutrino events. In Kamiokande, we observed 11 neutrino events within 13 seconds. In addition, other experiments, IMB3 and Baksan experiments, observed some neutrino events at the same time. So in total, these three experiments observed 24 neutrino events from supernova 1987. The number of events was only 24. However, these events were already large enough, number was large enough to understand the basic mechanism of the supernova explosion. Namely, we understood that when a massive star finishes its life, the star collapses, a shock wave is generated, and therefore the outside of the star is exploded. So this was what we understood. And based on this observation, Professor Koshiba received Nobel Prize in Physics in 2002. But of course, you already realized Kamiokande was extremely lucky we started the low energy data taking in January 87, and we observed supernova neutrinos in February 87. The previous supernova explosion that was visible by the human eye was 400 years ago. So many people said to Professor Koshiba that he was lucky. Well, hearing these kind of comments, he mentioned to people, and I'd like to tell you what he said. He said, many people say I'm fortunate. However, at that time, neutrinos came to everywhere on the Earth. Only people who prepared for them were able to observe them. So, well, I think we scientists and also future scientists, we should not forget about this kind of words from Professor Koshiba. Okay, well, now, actually, in addition to the supernova neutrino observation, Kamiokande had an important hint for the future neutrino experiments. One was the observation of missing atmospheric neutrinos. Kamiokande observed atmospheric neutrinos from the beginning of the experiment, and in 1988, Kamiokande published a paper that the number of muon neutrino events was much fewer than expected. Also, well, I'd like to recall you that Kamiokande started the modification, improvement for the study of solar neutrinos, and indeed, in 1989, Kamiokande successfully observed solar neutrinos, and at the same time, Kamiokande confirmed that the solar neutrino flux coming to the Earth was much fewer than expected. Here in this graph, around cosine theta 1, there is a peak, and this is the solar neutrino signal above the background shown by blue. But compared with the standard solar model prediction, the observed flux was indeed significantly smaller than the model. So, observation of supernova neutrinos 87, missing atmospheric neutrinos 88, and confirmation of missing solar neutrinos in 89 suggested that neutrinos should be very important. Therefore, the construction of Super-Kamiokande was approved in 1991. Now, I want to move on to the Super-Kamiokande experiment. And also, I want to talk about the atmospheric neutrino oscillations. Well, indeed, Super-Kamiokande is a much larger version of the original Kamiokande experiment. It contains about 50,000 tons of extremely clean water. And here I show a photo of the Super-Kamiokande experiment. And you see near the bottom of the photo, there are 3 people on the boat. So comparing the size of the people and the size of the detector, so you realize how big the detector is. And well, actually, in order to operate this kind of large experimental facility and analyze data from this facility, we need many, many, many people. So it's a large international collaboration of 230 or 40 people from 11 countries, including, of course, Spain. And well, now here I want to show you the photo that were taken during the construction. Well, these photos were taken in the summer of 1995. And well, during the summer, we are constructing the side wall of the detector. You may remember. when we constructed the Kamiokande experiment, we used both. But this time, we didn't use both because we thought the working condition and the efficiency was not good enough to construct the detector quick enough. So we did everything on the floor. But still, we needed many, many, many people to work on this. But anyway, once again, I enjoyed constructing the detector. Anyway, the construction work went well, and we started the experiment in April '96. And one of the scientific targets was the studies of atmospheric neutrinos. Well, actually, I already mentioned atmospheric neutrinos, but I didn't mention how these neutrinos are created. Well, as shown here, cosmic ray particles, high-energy particles, come into the atmosphere of the Earth, and they interact with air nucleus, and typically, after the interaction, pions are produced. But pions are unstable particles. They decay to other particles. And during these decays, neutrinos are created. And these neutrinos are observed in Super-Kamiokande. For example, this is a typical mu-neutrino event observed in Super-Kamiokande. So you see a ring pattern of the light. So this is a typical mu-neutrino event, and Super-Kamiokande observes about 10 neutrino events in a day, and we studied these events as a team. And, well, of course, we have a reason to seriously study these neutrinos, because, well, the original Kamiokande data suggested something interesting is going on in Kamiokande. In particular, we have been thinking that maybe the interesting neutrino data are due to neutrino oscillations. And here I very briefly introduce neutrino oscillations. Neutrino oscillations are the phenomena that was already predicted more than 60 years ago. And anyway, according to these theories, if neutrinos have mass, neutrinos change their type or flavor from one type to the other. For example, in this case, we assume that mu-neutrinos is created at x equals 0 and begin to propagate to the right. Then at some point, the probability that a mu-neutrino is remaining as mu-neutrinos go down, and at that point, tau neutrino is appearing. But if this neutrino continues to propagate, then probability that mu-neutrino to remain as mu-neutrino come back to unity. And at that time, tau neutrino is completely disappearing. So this is actually continuing. So therefore, we call this phenomena as neutrino oscillations. Now, we have been seriously studying atmospheric neutrinos if the missing atmospheric neutrinos were due to neutrino oscillations. And indeed, in 2 years, we were able to come to a very clear conclusion. Here I show 2 slides that we presented at the Neutrino Conference in 1998. In particular, please look at the left slide, by the way. This presentation was in the 20th century. In the 20th century, we didn't have PowerPoint. So, well, unfortunately, the presentation was not very clean. Anyway, this was what we did. Well, anyway, please look at the bottom panel of the left one. And, well, cosine theta means neutrino arrival direction, and cosine theta 1 means neutrinos coming from above. and cosine theta 1 means neutrinos coming from the other side of the Earth. And black circles with error bars show the data, and the hatched histogram show the Monte Carlo prediction, simulation prediction, where in the simulation we didn't include neutrino oscillations. Then you can immediately find for downgoing muon neutrinos, the data and prediction agreed very well. But for the upward going neutrinos, the number of observed data was essentially half of the prediction. So this can be easily understood if neutrino oscillate. And while propagating in the Earth, they change their type. Therefore, when they arrived at the Super-Kamiokande detector, the probability that muon neutrino is remaining as muon neutrino is just essentially 50%. So by this kind of data, we were able to convince the global neutrino community that neutrinos oscillate. In fact, there are some other supporting data. So anyway, by this data, we were able to convince the neutrino community that neutrinos oscillate. Now, well, I may not say too much about the story behind this discovery, but let me talk about a little bit about the story. Around 1986, in Kamiokande, we already found that the observed number of atmospheric muon neutrinos was significantly fewer than expected. And since then, we have studied atmospheric neutrinos to understand why the observed number was much fewer. Many researchers outside of Kamiokande were actually skeptical of the Kamiokande results on atmospheric neutrinos. But well, I was unable to forget about the problem. Well, to be honest, at the beginning, I thought that the missing atmospheric muon neutrinos might be due to our problem somewhere in the data analysis, or something fundamentally important. But well, at the beginning, I had no idea which was the right answer. Anyway, it took slightly more than 10 years to conclude that the missing atmospheric muon neutrinos were due to neutrino oscillations. And well, we think that we were very fortunate, very lucky. We discovered neutrino oscillations simply by trying to understand why the muon neutrinos were missing. So, well, indeed, we were lucky. Well, okay. I think it's my duty to talk about other results and activities of Super-Kamiokande. But from now on, I'm not very much deeply involved. Therefore, just I want to give you the general results from Super-K. Solar neutrino oscillations. Actually, well, although I said results from Super-K, but actually the main player of the solar neutrino oscillation discovery was not Super-Kamiokande. In fact, already in 1985, there was a proposal to understand the missing solar neutrino problem. This idea came from Herb Chen. He proposed to observe the total neutrino flux and the electron neutrino flux separately. And for this, he proposed a large heavy water Cherenkov detector. In fact, by using heavy water Cherenkov detector, it is possible to observe charged current events, which is only sensitive to electron neutrinos. In addition, heavy water can detect neutral current interactions, which is sensitive to all flavor neutrinos. Based on this idea, the snow experiment was constructed in Canada. So the sketch of the snow experiment is shown here, and in the flask, they contain 1,000 tons of heavy water, D2O. Well, maybe this part is too detailed, so I skip. So then, the initial evidence for solar neutrino oscillations came by combining the snow data and the Super-K solar neutrino data. The snow experiment observed solar neutrinos by charge current interactions. Therefore, they are only sensitive to the electron neutrino flux. Therefore, by charge current interactions, they cannot tell anything about the flux of the muon and tau neutrino flux from the sun. On the other hand, Super-Kamiokande observed solar neutrinos by neutrino electron scattering. Well, neutrino electron scattering is most sensitive to electron neutrinos. However, this process is also sensitive to muon and tau neutrinos with reduced cross-section. Therefore, the Super-Kamiokande data constrain the nu E flux versus nu mu plus nu tau flux in a slightly inclined way. And therefore, by combining the snow data and Super-K data, we begin to realize that there must be finite nu mu plus nu tau flux from the sun. Then, maybe one year later, snow had a neutral current result, and then the evidence for finite nu mu plus nu tau flux from the sun was very, very clear. And since the sun can only generate electron neutrino flux, this was the evidence for solar neutrino oscillations. So this way, snow plus Super-Kamiokande discovered solar neutrino oscillations. In addition, Super-Kamiokande has been used as the far detector in long baseline neutrino oscillation experiments. The first experiment was the K2K experiment, where the neutrinos were created at the proton synchrotron in KK and detected in Super-K. And in this experiment, K2K experiment confirmed oscillation of atmospheric oscillation of muon neutrinos. The next generation experiment is T2K. The neutrino beam is created at the JPAC accelerator facility. And indeed, this is, I would say, one of the world's strongest accelerator in terms of the number of protons accelerated. And therefore, the neutrino flux is very high. Therefore, T2K observed many neutrino events. And indeed, they observed muon neutrino to electron neutrino oscillation. Furthermore, T2K is trying to observe if there is any difference between neutrino oscillations and anti-neutrino oscillations. And indeed, T2K indicate that oscillation of neutrinos and oscillation of anti-neutrinos could be slightly different. And it's quite interesting. Anyway, after the discovery of neutrino oscillations, the world's neutrino community has been extensively studying neutrino oscillations. And here I list, maybe it's still an incomplete list, but here I list the neutrino oscillation experiments that contributed to our understanding of neutrino oscillations. So you find there are many, many large-scale experiments in the last 25 years or so. And in fact, by these activities, we understood neutrino mass and neutrino mixings rather well. And well, I'm not going to details, but now we really understand these oscillation-related parameters very well to an accuracy of 1% or, in the worst case, a few percent. But, well, certainly this accuracy is incredible. However, in my opinion, the most important part is shown here by red. First is neutrino mass is very small, probably more than 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. Neutrino mass are very, very small. Furthermore, we found that neutrino mixing angles are large, much larger compared with the corresponding quark mixing angles. And in my opinion, it's still a mystery why neutrino mixing angles are large. Well, before finishing Super-Kamiokande, I would like to talk about the recent activity in Super-Kamiokande. As I mentioned, Kamiokande observed supernova neutrinos in 1987. Actually, from the start of the Super-Kamiokande experiment, we have been trying to observe supernova neutrinos. Unfortunately, so far, after 30 years of the observation, we didn't observe any supernova neutrino burst. However, if we think about the history of the universe, there should have been many supernova explosions. And in each of the supernova explosions, really significant number of neutrinos should have been produced. And these neutrinos should be still traveling in the universe. And therefore, some of the neutrinos should come to Super-Kamiokande. So we are now trying to observe these diffuse supernova neutrino background, past supernova neutrinos. And by observing these neutrinos, ideally, we'd like to study the history of supernova explosion. In fact, unfortunately, the original Super-Kamiokande had a little too much neutrino background to observe diffuse supernova neutrino background. Therefore, Super-Kamiokande was upgraded to enhance the sensitivity to these neutrinos by dissolving gadolinium into the super-K water. Why we put gadolinium into super-K water? Because the signal is the nu-EBA interaction on proton, then neutrons are produced in addition to E+. Of course, we can easily observe E+ signal, but we cannot observe neutrons. But if we put gadolinium into the super-K tank, water, then these neutrons are captured by gadolinium, and after the capture, gadolinium emits several photons, gamma rays, and total energy of these gamma rays is about 8 MeV. And therefore, we could observe, these gamma ray signals. And by observing the coincidence of E+ and gamma rays, we can reduce the neutrino background significantly. So we put gadolinium into super-K in 2020, and we added more gadolinium in 2022. And in fact, the early data is quite promising. Here, I show the super-K data that was presented at Neutrino Conference in 2024. The horizontal axis shows the energy of the neutrino events, And the red histogram is the expected diffuse supernova neutrino background. And you see there's some excess around that energy region. And in fact, if, the left one is after putting gadolinium into super K, but if we combine all the super K data from the beginning, people found there is about 2.3 sigma excess above the background. So it's really exciting. So I'm looking forward to seeing the new result, maybe sometime soon. Now, I'd like to move on to the Hyper-Kamiokande project. Well, now, in the universe, well, there are, of course, many mysteries, but there's one big mystery. At present, the universe is dominated by matter particles. But at the beginning of the universe, during Big Bang, there should have been equal number of matter and antimatter particles. Then, after Big Bang, the universe expands, cools down. Then, what happened was matter and antimatter particles meet and annihilate, disappeared. So, we naively expect, at present, there should be no matter, no antimatter particles remaining. But of course, as this photo indicates, only matter particles remained. We don't know what happened. But there is an interesting idea, theoretical idea. Neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So, neutrino physicists were excited with this possibility. And therefore, the neutrino community is trying to get some hint to support this idea that neutrinos with small mass has the key to understand the matter in the universe. In fact, there are two big projects are going on under construction. One is called DUNE in United States. Another is Hyper-Kamiokande in Japan. Well, both are international collaborations. When I say United States or Japan, it simply says the location of the experiment. And with these experiments, we'd like to observe if neutrino oscillations of neutrinos and those of antineutrinos are different. Well, I mentioned to you that the T2K experiment already had some hint that there could be some difference. But, well, the statistical accuracy is not enough. Therefore, we need the next generation neutrino experiments, and therefore these are DUNE and Hyper-K experiments. By the way, since I'm from Japan, I'd like to talk about Hyper-K very briefly. Hyper-K is going to be a very large neutrino experiment underground. It's about 68 meters in diameter and 72 meters high. And the fiducial mass that can be used for the neutrino analysis will be about 8 times larger than the present super K. So because of this huge mass, we expect many important research topics in neutrino physics and astrophysics. And indeed, we have many collaborators from the global community. We have more than 600 collaborators from 23 countries. Here, I show a photo of the Hyper-K construction. The excavation of the underground cavity has finished in July last year. Now, people are constructing the water tank. And the experiment will start in 2028. So, well, neutrino physics are still very exciting. But let me move on to gravitational waves. Well, gravitational waves were first predicted by Albert Einstein in 1916 based on his theory of general relativity. For example, if there is a binary black hole system, then we expect a strong gravitational wave will be emitted from this system. Well, if a gravitational wave is emitted and if a gravitational wave comes to the Earth, the expected effect is the length change. Space can be extended or shrinked for a small amount. And actually, in order to observe gravitational waves, we use laser interferometers. Well, laser interferometers are a very good technique to observe a very small length change. Well, actually, I'm now working on gravitational waves. Therefore, here in this page, I would like to briefly tell you why I changed from neutrinos to gravitational waves. Well, first of all, I studied neutrinos for more than 20 years. And after the discovery of neutrino oscillations in 1998, and after some more studies for several more years, I was feeling that I finished what I should do in my neutrino research. Well, of course, as I mentioned, neutrino research is still very exciting, but I was feeling that my contribution to neutrino physics is kind of done. So I thought that way. And on the other hand, of course, there are still many exciting science that we would like to study. In particular, gravitational waves had not yet observed at that time, around 2005. And I was fascinated by the research on gravitational waves and the studies of the universe with gravitational waves. This is a completely new way of study of the universe. And well, then in 2008, I became the director of the Institute for Cosmic Ray Research. And well, at that point, it was clear that I could no longer contribute to neutrino research much. It was clear that I had to change my research style, work style significantly. But I still wanted to be involved in exciting research. Therefore, I decided to participate in the gravitational wave project, Kagura, with my partial time. And fortunately, the Kagura project was approved in 2010 by the Japanese government. Well, okay, then in 2015, LIGO in United States observed the signal of gravitational waves with the two laser interferometers. And here show the data from these two laser interferometers. And from these data, they concluded that this is the real signal. And data told us that two black holes of 36 solar mass and 29 solar mass merged at a distance of 1.3 billion light years. And people are really excited, and we indeed think this was really great discovery. And at that moment, the gravitational wave astronomy was started. And indeed, a Nobel Prize in Physics was awarded already in 2017. By the way, at the bottom of this slide, I show the photo of the two LIGO laser interferometers. And you see, this is, again, a very large facility. In fact, it has a 4 kilometer by 4 kilometer arm length. And still, it's the largest laser interferometer facility. Okay, that was slightly more than 10 years ago. Since then, LIGO and Virgo in Europe continue observing gravitational waves, and this is the summary of the gravitational wave observation by until January 16, 2024. In about 10 years, a total of 218 gravitational wave events were observed. By the way, the vertical axis shows the mass in unit of solar mass, and blue circles show black holes, and orange circles show neutron stars. And please forget about yellow and red ones. Anyway, most of the gravitational wave events are merger binary black holes, but there are several binary neutron star and neutron star binary neutron star black hole mergers. So now we are really observing many gravitational wave events. Then you may ask, what would you like to know with these observations? Well, at present, the main scientific topics are maybe these three: observation of the merger of binary neutron stars, merger of binary black holes, and supernova explosions. And indeed, there are many sciences, important sciences, but let me talk about the first one, merger of binary neutron stars. And in fact, we think these are very important objects, because we think seriously that the merger of binary neutron stars are the origin of the heavy metals in the universe. I mean, gold or something like that. We believe that are generated with these events. In addition, well, neutron stars are still very important scientific topic. We would like to understand the inside of neutron stars. So we would like to use gravitational waves to study the details of the neutron stars. Anyway, there are very important scientific topics. Therefore, we have been working hard to contribute to the gravitational wave astronomy with Kagura. But unfortunately, as I tell you later, we are still in early stage. Therefore, I'd like to tell you what we have been doing, what we did, and what we have been doing. By the way, Kagura is an international collaboration. We have collaborators from 9 countries and regions, about 150 authors. And you may find these countries are actually, many of these countries are actually from East Asia. Anyway, Kagura is another large laser interferometer. It has 3 kilometer by 3 kilometer arm length, and it is located underground. Whole laser interferometer is located in underground. In fact, there is a reason we construct a laser interferometer underground. In underground, the seismic activities are much smaller compared with the surface. And in fact, seismic activities are very serious background noises to the observation of gravitational waves. Therefore, we decided to go to a place where the seismic activities are small. Therefore, we decided to go underground. Well, here I show several photos of the construction of the Kagura laser interferometer. For about 10 years, we worked hard to construct the Kagura laser interferometer in underground. So, for example, in the left bottom, you see the 3-kilometer vacuum tube. And in the middle, you see one of the main mirror of the Kagura, which is a 23 kilogram sapphire mirror, which will be actually cooled down to 20 to 30 Kelvin. And in the right, I show a photo of the mirror installation into the vacuum tube, vacuum tank. So for 10 years, we worked like this. And then we joined the global network of the gravitational wave detectors. In fact, we think it's very important that these laser interferometers work together, because to determine the location or direction of the source, we need at least 3 detectors, which are located far apart from each other. Even if you have a very, very, very good laser interferometer, but if you have only one laser interferometer, you have no idea from where the signal came. Only when we have 3 detectors, then, because the gravitational wave comes with the speed of the light, then we see the arrival timing difference. And by using this information, we can show the location from where the gravitational wave came. And in fact, this is important because, well, we have to tell the optical telescope people to see the very important event. Anyway, because of this importance, LIGO in United States, Virgo in Europe, and Kagura in Asia work together. Namely, we observe gravitational waves simultaneously, sharing the data and analyzing the data as a team. And well, Kagura is, of course, is a much newcomer, and therefore, Kagura still have to spend a lot of time to improve the sensitivity. Anyway, Kagura rejoined the observation on June last year. Well, in fact, I wrote here. We had, before the start of the observation, we had serious damage by a local earthquake on January 1st, 2024. Anyway, we recovered from this earthquake, and we joined the observation last year. But unfortunately, still, the sensitivity is not good enough. We still have to improve the sensitivity further. Well, okay, that is the status. But before finishing, I'd like to tell you what we are thinking about the future of Kagura in the 2030s. Well, as I mentioned, one of the most important targets in the near future could be the observation of the binary neutron star mergers. And this is a simulation, and the simulation of gravitational waves. And well, for some cases, even after the merger, there should be a ultra-heavy neutron star remaining for a short time. Then after some time, this ultra-heavy neutron star collapsed to a black hole. So, in fact, just before the merger and just after the merger, there is very important physics there. So, Kagura decided to improve the sensitivity in the kilohertz range to be able to observe these kind of gravitational wave signals. And with this improvement, we'd like to study the neutron star mergers. In addition, this frequency range is important for the study of supernova explosions. And finally, if possible, we'd like to observe subsolar mass black holes. We don't know. Okay, let me summarize. Neutrinos and gravitational waves are very important for unveiling the secrets of the subatomic particles and the universe. And experiments in Kamioka have been contributing to these studies. But I believe many more fundamental discoveries will be ahead of us. Okay, that's all from me. Thank you very much.
Thank you, Professor Kajita. It was a very nice revision of your work. It was truly impressive. And now it's time for our audience, if they have any question they may have. So.
Hello.
Hello.
If you want to detect like upcoming neutrinos and downcoming, isn't more efficient if instead of a cylinder, it's like more the area of the top and bottom is bigger?
Thank you for this question. Well, in fact, it's important to know the energy of these neutrinos. But in order to measure the energy of neutrinos, we have to measure the energy of muons. And in fact, in order to measure the energy of muon, we have to measure how long they travel in the detector. Therefore, thin detector may not be good. I think still the cylindrical detector is a good option.
Hello. How many solar masses do you need of two black holes so you can see the distortion with your bare eye?
So, say again?
How massive have to be two black holes so you can see the distortion of the space-time with your eye?
My eye?
Yeah, your.
Well, okay, thank you for this question. Oh, well, yeah, well, I don't know the exact answer, but I would say, in order to see this distortion of space-time by eye, I believe we have to observe black hole mergers in the next room. Then, of course, you die. You cannot. You cannot escape.
Thank you for your talk, Professor Kajita. I have two questions. Who and how did that person come up to the idea of oscillating neutrinos?
Mm-hmm.
And is there any other subatomic particle that shows the same behavior apart from neutrinos? Thank you.
Thank you. Well, the persons who came to neutrino oscillations are shown here. Bruno Pontecorvo and Maki Nakagawa Sakata.
And the second question was? If there are any other subatomic particles that do the same, that oscillate in the same way, that can change one flavor from one flavor to another.
Okay, it's actually I'm not sure. There is a phenomenon called K-long and K-short, K-on system. Yeah, but I already forgot about this.
There are some other systems.
Yes, thank you. There are other systems which are mesons, it means particles without spins, and in particular these are named kaons, which are much heavier particles, and these particles exist in different states, and they also have this, it's not exactly the same, but they also have this possibility to be in different states and change that. But this is basically what I know.
Hello, thank you. I would like to ask that you are an important profile for the scientist community, and I would like to ask, what would you say to our young community to motivate them in the future years due to your Nobel profile? Thank you.
Thank you. Well, we have many, many, many more mysteries in the universe. And these mysteries are waiting for you to tell us the secret. So, please.
First of all, thank you for your talk. And my question is, what is the relation between mass and this behavior of oscillating particles?
Oh, mass and oscillation.
Yes.
Thank you. In fact, this page shows. Well, if the neutrino mass is smaller, the oscillation length gets longer. So by measuring the oscillation length, we can get the information on the neutrino mass. Well, more exactly, neutrino mass difference. But anyway, information on the mass.
Okay, but my question is really, why does this oscillating behavior occurs?
Why this oscillation behavior occurs? Okay, okay, thank you. Well, well, I have to tell in 30 minutes. Well, okay. 30 seconds, sorry, 30 seconds. Well, there are three neutrinos. Muon neutrinos, electron neutrinos, and tau neutrinos. In fact, according to quantum mechanics, they do not need to have unique mass. In fact, both electron neutrinos is actually we believe, combination of the three neutrino mass states, muon neutrino and tau neutrino as well. Then, for example, if this electron neutrino begin to propagate in the space, then these three mass states coherently propagate in the space. However, the three mass states have a different mass, of course, and therefore the way of the wave development is slightly different. Then that means after some point, this original electron neutrino can no longer be pure electron neutrinos. And if you calculate, you find that some other flavor is appearing.
Thanks.
Hello, Alan. If the flavor change and they have different masses, that doesn't change the energy of the neutrino beam or neutrino?
No. Well, neutrino type change, but fundamentally, three mass eigenstates propagate coherently. No energy change.
But the mass is different.
Mass is different, but they are just coherently propagating.
Okay.
Hi, Professor Kajita. Thank you for the exposition. And my question is, how do you translate the neutrinos information to see, for example, the gravitational waves from the binary system?
Mm-hmm.
Yes. How do you translate the information that neutrinos give you about the, for example, the binary system of neutrino stars?
I got confused. So is your question, are there any connection between neutrino physics and gravitational waves?
Yes, how do you translate the information? My question is, how do you translate the information that neutrinos give you about the gravitational waves?
Oh, your question is about the experimental technology in neutrino physics translated to gravitational wave detection, or?
Let's move to another question, and then we come back, okay?
Yeah, maybe, yeah.
Oui, ahora. Hi, very nice to meet you. One question about the gravitational waves. How does the gravitational waves from binary neutron stars relate to the origin of the metals?
Oh, thank you. Yes, it's a very important question. Well, okay. In fact, this is a simulation of the merger of binary neutron stars. And well, maybe soon you may find that neutron stars kind of break and substantial matter are emitted. And these matter are actually very neutron rich. And therefore, these neutrons are captured by other nuclei. And therefore, heavy nuclei, very neutron rich, is produced. So this process is occurring, and by rapid neutron captures, heavy metals are generated. That is what we thought. But answering to your question about assuming that what I learned in neutrino physics is transferred to gravitational wave physics. Well, okay. I think the experimental technology is actually quite different. Therefore, as far as that experimental technology is concerned, I think I have not much transferred to the group. However, I would like to say one thing. Well, at least in Japan, neutrino community had advanced earlier. Therefore, they have, including me, they have experience in working in large collaborations. On the other hand, the gravitational wave community was smaller. Therefore, they didn't have experience working in big collaborations. Therefore, this kind of information was transferred to the gravitational wave community, at least in Japan.
Hello, professor. My question is if the standard model of particles was able to predict the existence of these flavors and these masses of the neutrinos or not, or it's a completely experimental discovery?
Okay, thank you for this question. Well, first of all, standard model of particle physics simply assumed that neutrinos are massless. And therefore, well, first of all, the observation of finite neutrino mass implies something beyond the standard model. And in fact, a very small neutrino mass implies the existence of very heavy neutrino-like particle that we can never see. Anyway, this kind of heavy particle implies the new energy scale of new physics, and therefore we think neutrino mass is important.
Hi. Thank you. I would like to ask, the fact that neutrino exists should mean that antineutrino also exists. And so, have you seen in your project the oscillation of antineutrinos, or do you know if that occurs?
Thank you. Yes, actually, I briefly mentioned about the T2K experiment. Neutrinos are created in the JPAC accelerator. In fact, in this accelerator, people created neutrino beam plus antineutrino beam. And people observed oscillation of neutrinos and oscillation of antineutrinos.
Hi, thank you for your presentation, first of all. I would like to ask, from your detectors in Kamiokande and Super-Kamiokande, which are photodetectors, I believe, how do you differentiate what flavor of neutrino you're detecting?
Oh, thank you. Thank you for this question. Okay. An electron-neutrino interaction produces electron. A muon-neutrino interaction produces a muon. Then the question is, how can we differentiate electrons and muons in Kamiokande? In fact, these particles must propagate in the water, but electrons have a small mass. Therefore, they are essentially ultra-relativistic. And therefore, electrons produce electromagnetic shower while propagating in the water. But muons rather heavy, therefore they simply go straight. So by observing the difference in the observed Cherenkov ring pattern, we differentiate electrons and muons. In fact, we are very powerful. In Super-Kamiokande, we can separate these two particles with an efficiency of about 99%.
Hello, thanks so much for your talk. It's great to have you here. I have more like a practical question. So you said that there are many detectors. You went from a smaller Kamikande to bigger ones. And my question is, actually, how do you get there physically to the detector? Because they are like underground. People need to move there. They need to live somewhere. So my question is, how do you approach the detector?
Well, okay, thank you. Well, in fact, in original Kamiokande, we constructed the detector in an active mine. So in 1,000 meters underground, there was an active mine activities. So we constructed near to the active mine region. Then in Super-Kamiokande, well, already at that time, mine company decided to stop the activity of mining. But still, according to the Japanese law, they have to keep watching the whole mountain. Therefore, we asked the mine company to make the road from entrance to this Super-Kamiokande.
Thank you very much for the nice talk. So my question is concerning, maybe I could help the student with my question. My question is concerning after the gravitational wave signal, you get also a light curve coming from the kilonova signal, right? Out of the neutron star merger. Would it be possible to detect also neutrinos out of these events, or?
Oh, thank you. Yes. If the neutron star mergers occur in the Milky Way galaxy, I think neutrino signal can be observed. Unfortunately, the event rate of the neutron star merger in our galaxies, I don't know. Once in every 100,000 years, million years, I don't know. So very rare. Therefore, practically, it may not be possible in the near future, at least.
Hello, thank you for your presentation. I think it was really awesome. At the beginning of the presentation, you said that neutrinos with energies of about 10 mega electron voltians could be observed. What do you mean by observe if it's so little? And,
thank you.
And how do you know they have 10 mega electron voltians? And yeah, I think it's pretty abstract to imagine.
Yes, thank you, thank you. Well, certainly, of course, we cannot observe neutrinos. We can only observe neutrino interactions. A neutrino may interact with an electron, producing electron, and we observe the signal produced by electron. And well, in fact, there is a correlation between neutrino energy and the electron energy. Therefore, by measuring the electron energy, we can statistically estimate the neutrino energy.
Hello. First of all, thank you very much for your presentation. And my question is, at some point in the presentation, you said that at the beginning of the universe, there was an equal amount of matter and antimatter. My question is, why do you think that neutrinos play an important role in imposing that today we have mostly matter in the universe?
Yeah, okay, thank you. Well, why neutrinos are relevant? Well, okay. I said, in order to explain the very small neutrino mass, typically we introduce neutrino-like particle, but extremely heavy. And these extremely heavy neutrino-like particles should existed in the Big Bang early universe. And the point is, these particles are unstable and decay to other particles. And during this decay, there must be the original source for the matter and antimatter asymmetry. Okay.
Hello. First of all, thank you very much for your presentation. It was truly remarkable. And I want to ask you if the detection of solar neutrinos is very dependent on the solar energy throughout the years, or is mostly a background that is very stable so that you can actually perform experiments during the year, or maybe, for example, a solar flare or an event occurring in the center of the sun has a huge impact on the number of neutrinos that you receive in that moment.
I'm afraid I may not understand your question completely. Well, certainly, the observation of solar flare, neutrinos related to solar flare, is actually important scientific topic in Super-Kamiokande. some people are trying to observe them, but no success yet. Essentially, in Super-Kamiokande, we only observe neutrinos produced by nuclear fusion processes at the center of the sun. And they are essentially very, very stable.
Professor, is possible to detect a hypothetical proton decay with Super-Kamiokande experiment?
Oh, thank you. In fact, well, certainly in Hyper-Kamiokande, because we have more water in the tank, that means we have a better chance to observe proton decays compared with Super-K. And, well, people are thinking if true proton lifetime is shorter than 10 to 35 years, after 20 years of observation, we may have rather good signal.
Hello, Professor Kajita. It's a pleasure to hear you. Thank you for being here. I wanted to ask you about the gravitational waves. If these events are produced by, if these ones are produced by high energy level in the universe, how could this new way of observing the universe help us to research about that dark age of the Big Bang where photons couldn't escape?
Last part.
Yeah, how could these gravitational waves help us to research about the dark age of Big Bang where photons couldn't escape?
Yeah, thank you. In fact, in my opinion, gravitational waves are very important to really observe the dark age of the universe. Well, present generation of gravitational wave detectors are not powerful enough, but the next generation of gravitational wave detectors, which are planned in Europe and United States, they are indeed extremely powerful. For some black hole mass, they can observe gravitational wave, and they can observe merger of black holes up to redshift 100. So, indeed, these future gravitational wave detectors will be very important to understand the history of the universe.
If one neutrino interacts with another neutrino, would like oscillate in flavor?
Neutrino interact with the neutrino?
Like if one neutrino interacts with another one, like if they hit one to each other. Because, I don't know, I thought that like, because they, in the sun there is a lot of neutrinos generated, I thought that maybe on one between a billion, they like maybe interact, they will oscillate in flavor or something like that.
Yeah. Oh, yeah. Well, okay. Well, in principle, neutrinos can interact with neutrinos. Yes. And in fact, this can be a very important phenomenon to understand because, well, for example, in case of supernova explosion, at the center of the star, the neutrino density is extremely high. Therefore, the neutrino interaction could play a very important role. So this is a very important topic, and I don't know if we have already come to a very clear idea of what happened on these cases. I think people are still seriously studying these phenomena. Yeah, yeah.
Hello, I have another question. Because the topic of the early universe history was mentioned, and I was under the impression that there exists a cosmic neutrino background that should exist as a remnant of the early history, like 2 minutes after the Big Bang, not like the cosmic microwave background. And my question was if there's any hope to ever detect experimentally this background, or is something that it's not really possible with our technology.
Thank you. Well, as far as I know, no one has a good idea yet. Maybe you, younger generation, to think about the detection of these cosmic neutrinos.
Hello, I hope you're enjoying your time here in Seville. I want to ask you, like, you talk about, right now we can predict the difference between the neutrino mass states, but how is like you choose the hierarchy? Like, how do you choose which is the heavier mass state right now?
Thank you. Thank you. It's in fact a very important question. Well, let's say there are 3 mass states, nu1, nu2, nu3. And we already know that nu2 is heavier than nu1. But we do not know if nu3 is the heaviest or the lightest. This is still an open question. And on the other hand, we know in what kind of experiment we know this kind of ambiguity. So I hope within the next 5 to 10 years, we have a clear idea if nu3 is the heaviest or the lightest.
Hi, thank you for your talk. I would like to ask, how can you difference between, how can you tell that the gravitational wave you are measuring is from an exact event and not from other events in the universe that are causing interference in the measurement?
Thank you. Indeed, this is a very important question. And in fact, yes, in actual gravitational wave experiment, this is really important to really separate the background and the real signal. And therefore, we have actually many, I don't know the exact number. Even in Kagura, maybe we have already more than 10,000 monitors. And if we see some gravitational wave-like signal, then we have to check if there's any correlation with any other channels. So this kind of extensive monitoring is installed in all the gravitational wave detectors. And well, already we believe now our monitoring system is good enough to separate the signal and background.
Hello, thank you so much for your presentation. My question is more like a hypothetical one. As you have studied the smallest and the biggest things in the universe, do you think we are closer to unify gravitational theory with subatomic particles? As like with the neutrinos study, we couldn't exactly measure the thing that the standard model predicts. As you said, neutrinos were believed to be massless, but we have proven otherwise. Do you think the studying gravitational waves will help us create the unified theory?
Thank you for this question. Well, difficult to answer, really. I have no idea. Sorry.
Hello. Thanks, first of all. My question is how our University of Seville, got involved in the investigation and which role played in that?
The role of the University of Sevilla in Hyper-K? Or
I mean, I have understood that our colleagues, our professors from here participated in the development and in the studies of neutrinos and everything. So how started the participation in the project and the relationship?
Okay, thanks for your question. Yes. Okay, thanks. Let me tell you basically the story. We have here in Seville a theoretical group in neutrino physics. It's a small group. But then at some point, I had some PhD students, and one of them got a research project funded by the European Commission just to start collaborating with T2K. It was one of the experiments Professor Kajita mentioned, and Super-Kamiokande. So we got this research project, and therefore, because of that, a professor is over there. So he spent 2 years there in Japan and 1 more year, and then we started this collaboration. So how do we collaborate? Basically, we are involved in the analysis of data, just coming from the these T2K experiments. So we got in touch with all the team there, and we also participate in publications related with the analysis of data. And because of that, we also ask for the University of Seville be just official member from the international collaboration. So right now, the University of Sevilla is a member, a scientific member on this T2K, and we have been also asked to be member of this Hyper-Kamiokande, so the next generation. So this was the story. So right now, we are there, and I hope to have more students to continue this adventure.
We have time for one more quick question.
Hello again. Could strong gravitational fields influence neutrino oscillation while they propagate?
Oh, okay. I have never thought. I don't know the effect of strong gravitational wave, strong gravitational potential on neutrino oscillations. I don't know.
Okay, thank you very much, Professor Kajita. It was a real pleasure to have you here. And I would like to take a photo with all the audience, if you don't mind.
Okay.